So far, we have seen the convective heat transfer for external flows or flat surface or cylinders or spheres in cross-flow. And now we would like to look at the convection that happens in internal flows such as pipe flow. And first, let's look at the hydrodynamic boundary layer for internal flows. So for external flow, let's say flow or flat plate, the boundary layer can grow without any restrictions. However, when we have internal flows, the fluid and boundary layer are confined by surface. So let's say we have this long pipe. Let's say we have this circular tube, and there is a uniform flow that is getting into the tube. Let's call that U infinity. And what happens here, when it gets into the flow close to the surface, we have a no slip boundary condition. So the velocity is going to be 0. So if I plot the velocity profile, here initially the velocity is going to be 0. And then we see the effect of this no slip getting propagated inside the flow. And that's going to be the velocity profile. Now, if you go further down the pipe, the influence of this 0 velocity is going to be further noticed. Get symmetry here. Now, if I connect the point that the effect of these surface or 0 velocities are felt, first of all, the surface is a circular tube. So everywhere we have this surface around the fluid. Now for this 2D sketch, I'm just showing at the top and bottom side. But then what you're gonna see, formation of boundary layer around the tube. It's going all over. So this is gonna be the boundary layer that we have for the internal flow. And I'm gonna call this one as X, F, D, and H. So this is the entry, the entrance or the entry for the hydrodynamic or for velocity. So that's what we refer as a hydrodynamic entry length. Now, what happens here is after this entrance or the velocity after this entry length, the velocity profile does not change with x. So if I plot further the velocity profile beyond the entry length, beyond this this boundary layer formation, then we have what we call is fully developed velocity profile. And what I'm plotting here is this fully developed velocity profile for a laminar flow. So that profile does not change anymore. So this is the region we call as a fully developed region. Now, for turbulent flow, we are going to have exactly similar situation In fact, the velocity profile does not really look like each other. They're supposed to be exactly the same. So unchanged. I guess this is more representative. Now for the laminar flow, this velocity profile will be parabolic. So velocity profile in the fully developed region for laminar flow has a parabolic shape, and for turbulent flow, the velocity profile is more flatter, I would say. And that's because of the turbulent mixing that we have in the radial direction. So these are the few characteristics of the hydrodynamic boundary layer development in a pipe. We have this entrance length, that we have a development of this boundary layer, and then propagation of this zero velocity from the surface into the mainstream. And we have a point that the effect of boundary is felt all over the flow. And now the difference here between the external flow and internal flow is that for external flow, what you would see here is always we have this free stream on top of the boundary layer. Here, the boundary layer is kind of like bounded, and beyond a certain point, as we call it hydrodynamic entry length, we have this fully developed region. Now, we distinguish between laminar and turbulent flow by Reynolds number. So we define a Reynolds number based on the diameter of the pipe. So RED would be rho UMD over mu. So D is the pipe diameter, and UM is the mean velocity. And I will explain what is the mean velocity here. It's like mean velocity over the tube cross section for the cross section. Now for the fully developed flow, Reynolds number what we have a critical Reynolds number, RED, and critical is 2300. And that's going to be, if the Reynolds number is below that one, we're going to have laminar. So that's the transition from laminar to turbulent regime. Of course, it depends on the conditions that we are running the experiments. So Reynolds number of critical could go really higher than that, but as a rule of thumb, we consider around 2300 as a laminar. Hydrodynamic entry length. So just recall that this is the hydrodynamic entry length that we are looking, XFDNH. So the length of fully developed for the hydrodynamic, what we have is, we generally show that as a ratio with the pipe diameter. For the laminar flow, it depends on the Reynolds number. It's going to be 0.05 Reynolds number D. This is for the laminar flow. And this hydrodynamic entry length for the turbulent regime, it's going to have a range like between 60 and 10. And that's for the turbulent flow. For the sake of this course, we almost have most cases at a fully developed flow. We don't really deal with this interrelance for the heat transfer coefficient. The mean velocity that we use for the Reynolds number is defined based on the volumetric flow rate, or sorry, mass flow rate. So m dot is going to be rho u x and r dr, or sorry, DAC, cross-sectional area. The integral of that over the area, which we consider that as a rho AC UM. So we are integrating the whole, like let's say if we have this pipe flow, and this is the velocity profile, we are replacing that velocity profile with a mean that is a uniform. So this is going to be UM. That's going to give us exactly equivalent mass flow rate that we have in the system. So from the definition, UM would be the integral of rho u x and r dAc divided by rho AC. And if let's say I consider this one as a r direction, let's say this is x direction, we know in the fully developed regime u is not really a function of x, but I'm going to keep it there. So it's going to be integral 0 to r0 rho u, and the cross-sectional area is going to be 2 pi r dr. Cross-sectional area, the incremental of that dAc divided by rho pi r0 square. And if I just cancel out density pi, so UM by definition is going to be 2 divided by r0 square, integral of 0 to r0 ur dr. And depends on the velocity profile that we have, we can evaluate the mean velocity. So this is the mean velocity over the tube cross section.